Hello everyone, my name is Xingyu. I'm currently a postdoc at the Harvard University. Today I'm presenting our paper, Interval Change Point Detection for Runtime Probabilistic Model Checking, which is a joint work between my team at Harvard and two colleagues from the University of York. This work was supported by two large-scale UK projects on the safe use of robotics and autonomous systems. They are OCA-Hub and Assuring Autonomy International Program. Probabilistic model checking is a powerful formal technique to verify quantitative properties, and runtime probabilistic model checking has been widely used as part of the controller of self-adaptive systems to continuously verify if some non-functional requirements are satisfied or not for a given system configuration. And a fundamental problem here, or for any formal verification method, is how can we accurately describe the system behavior by some formal models. And in our case, that's the Markov chain model. And one solution is to model the system using interval Markov chains whose transition parameters are intervals. They are more robust because of the ability to capture uncertainties. Well, all existing state-of-the-art estimators cannot probably deal with sudden change, which motivates this work. So what is probabilistic model checking? It is a formal technique for verifying quantitative properties like reliability and performance of systems characterized by stochastic behaviors. And I'm using this figure I found on the website of Prism, which is a very popular model checker, to present the basic ideas and steps of doing probabilistic model checking. First, we need to formalize the system behaviors by Markov models like DTMCs, CTMCs. Second, we need to specify the system requirements, that's the properties to be verified in some logic language. Then we need to input both the system model and the formal properties into some model checker like Prism or Storm. We can know if the properties are satisfied or not. Or simply we can query the model checker, what is the quantitative result of the properties of our interest. Now the question is how to formalize the system behavior. Is your formal model accurately reflecting the real world? To answer that, in our previous work, we proposed a new Bayesian estimator using imprecise probability with sets of pairs, and we say IPSP for short. IPSP allows the modeling of vague and imperfect knowledge. Essentially, instead of assuming a single pair distribution, IPSP uses a set of pairs. Therefore, it gives a set of posteriors, and from that set of posteriors, we may determine the maximum and minimum values that gives us interval estimates. And a feature of IPSP is that the width of the interval provides a measure of the estimation errors, and by monitoring the growth of the interval width, IPSP may detect the prior data conflict phenomenon, which is what you believed is conflicting with what you observed. So as you will see later, this is a very important feature in our approach that used as the trigger for the online change point detection procedure. Also, it's worth to mention that IPSP has two versions for both transition rates in CTMCs and transition probabilities in DTMCs. However, a problem of IPSP and any other estimators is that the slow convergence to the new ground truth value after a sudden change. And the right-hand side is a quick example. Now let's properly define the interval change point detection problem. Say Pij is the transition probability of interest from state I to state j, and it is online estimated by the IPSP estimator. We assume all transitions within the Markov models are monitored and recorded, where the W is the number of total outgoing transitions from state I, represented by those circles in the figure. And those red circles are the actual transitions from state I to state j, The variable x represents the unknown change point, which is essentially an index of the transitions in the data window. Also, for a given x, we can know the number of right circles before and after the index x, denoted by NOx and MOx respectively. And now, given a data stream like this, we ask three questions. First, if the value of Pij experienced a sudden change. If yes, where is the change point? That is the estimation of the variable x. And finally, because we want to use IPSP to get bounded estimates, we need to ask what are the new priors used for the IPSP after the change point. For the change point detection procedure in our ICPD approach, first we can write down the likelihood function as this equation 7, where a and b are variables representing the transition probability before and after the change point x. Essentially, the likelihood function 7 is a product of two binomial likelihoods. The first one represents what happened before the change point, that is, seeing NOx success in X Bernoulli trials, while the second one represents what happens after the change point, that is, seeing MOx success in W-X Bernoulli trials. We can see there are three unknowns in our likelihood function. Having three unknowns in this procedure is not good enough for many reasons, like how to choose a multivariate price distribution, which seems impossible in practice and will not introduce huge bias in the estimation, or the cost of the determination of the posteriors for three unknowns is normally higher than, say, one unknown. Therefore, in our solution, we further reduce the three unknowns to one by introducing two relations. That is to replace the unknown parameter A and B with their MLE estimates. The justification of using MLE for A is from the IPSP estimator, we know there is no prior data conflict before X, so the data collected before X is good enough to use. And the justification of using MLE for B is after the change point, we have no knowledge at all about the new value of the transition parameter. So the best strategy is just to let the data speak for themselves. And now we have reduced the unknowns in the likelihood function from 3 to 1, which is the L sub x function in the equation 11. Since we have no prior knowledge of where the change point is, we can use a uniform priors for x as well, and we obtain the posterior as the equation 11. To determine the posterior distribution of x, we use the Markov chain Monte Carlo method, we say MMC for short, to generate a sequence of k samples of x. Since we have the relation between the variable b and x, we can also derive a sample sequence of b. From these two sequence of samples, we can answer three questions on the interval change point detection problem we defined before. That is, we can check the shape of the distribution approximated by the x sample sequence and decide if it indicates there is a change point with high probability at somewhere. And the maximum and minimum values in the set of B samples indicates the new price for resetting the IPSP estimator. Now let's have a look at the overall workflow of our ICPT approach. First, we start with the IPSP estimator, which takes some prior knowledge and runtime observations. Their exact forms are expressed as equations in the paper, and the same to other information flowing in this workflow. The IPSP estimator at the step 1 generates interval estimates, and we monitor the interval width to see if there is a prior data conflict at the step 2. If no, we feed that interval estimation into an interval probabilistic model checker to verify system-level properties. And if yes, then the change point detection analysis procedure is triggered at the step 3. It estimates a change point happened in the past timeline and redo the IPSP estimation from the past change point to now in a retrospective way. That's the step 4. Also, it starts new IPSP estimates from now with the new priors and observations. That goes back to the step 1 again. And this loop will continue until the end of the operation of the system. We have evaluated our approach by performing extensive experiments. The first one we study is about accuracy, in which we studied 9 scenarios. Because of the time limit, I can only present you in detail a typical one we call a big step change. It is a big step change in the sense that the ground truth transition probability, represented by the red lines, jumps from 0.3 to 0.7 at the time step 500, which is the ground truth change point to be estimated. First, we can see before the change point, IPSP did a good job to give us bounded estimates. And not long after the change point, IPSP estimator detects a prior data conflict and triggers the online change point detection analysis at the time step around 700. That is the blue vertical line in the figure, and use a estimated change point at 504, which is very close to the ground truth 500. That's the yellow vertical line, and you can see it is basically overlapping with the vertical red line. Now our approach resets the IPSP estimator in a retrospective way from the estimated change point to the trigger point, that is the dashed curves, and then continues the estimation until the end of the operation. That's the solid curves after the blue vertical line. For a comparison purpose, we also present the IPSP results alone without the new ICPT analysis. That is the dotted curves after the blue vertical line. And we can see without our ICPT approach, IPSP estimator alone is far off from the ground truth after the change point. What I have just presented is only one of the 9 scenarios we studied. As you see here, we have also studied medium steps, small steps, a slow recovery change where the ICPT procedure was triggered twice, and a quick recovery change, a steep ramp change, a slow ramp change, a earlier step change, and no change at all. Yes, as you can see, our ICPT didn't trigger in some cases, like for a small step change, that's the scenario C, and a quick recovery change, that's the scenario E. This could be either a good thing or bad thing, depends on the application requirements. For instance, in a application, we may treat the quick recovery change as some random noise and tends to ignore them without taking any action. Well, if we want to capture such subtle changes, it's okay. We can still configure the ICPT, and that's the next research question. Essentially, we have 2 means to configure the ICPD approach to be most sensitive to subtle changes. First, we can add a sliding window to the data stream so that we can discard the old data and put more weights on the new data. We can see by doing this, now the small step change is captured in the first figure below. Alternatively, we can use relatively more precise prior knowledge, because the newly collected data conflicts more easier with the more precise prior knowledge. And by doing this, we see now in the middle figure, the quick recovery change is captured. Of course, by making the ICPD more sensitive, we are at the risk of seeing false alarms. For instance, in the third figure, where there is no change at all, we still triggered 4 false alarms. The good news is, even if a false alarm was triggered, the ICPD can reject this false alarm after seeing a very flat posterior distribution of the change point X. And also importantly, the overheads of our ICPD is low, which is the next research question. Here we study the overheads of our ICPD approach. First, we know that the computational cost of the IPSP estimator and its trigger is in constant time and can be ignored, since they are all based on simple closed-form results that we have shown in the paper. And the only bottleneck factor of our ICPD efficiency is the number of MMC trials conducted when determining the posterior distribution of the change point. Based on the experiments in the first figure below, we found out the time is basically linear to the number of MMC trials conducted, and the number of trials is more than around 2000. The change point error is small enough, as shown in the second figure. On my 4-year-old laptop, if we do 2000 MMC trials, our approach can finish in 0.2 seconds, which seems fast enough. Finally, we did a case study reusing a robotics exemplar called Undersea to examine how our approach supports the verification of system-level properties. In Undersea, essentially we're simulating an underwater vehicle surveilling mission. There are sensors mounted on the AUV and collecting data on some oceanic parameters at some frequency. There are system-level requirements like a sensor must take at least 20 accurate data points per 10 meters. In this study, we injected a fault to a sensor at time 300 seconds, which caused the reading rate drops from 6 Hz to 2 Hz, and our ICPD approach captures this sudden change and propagates it to the system-level verification, showing that the requirement 1 is being violated. That's the shaded area in the figure. To conclude, we introduced ICPD as an online change point detection technique that tailored for runtime probabilistic model tracking applications using interval Markov chain models. It is essentially composed by 2 parts: a robust Bayesian estimator on Markov model parameters and a lightweight Bayesian change point detection procedure. The 2 Bayesian components are assembled in a loop with automatic trigger rules to invoke each other. And in the future, we plan to investigate more types of changes and work on how to elicit prior knowledge for the Bayesian estimators in a more rigorous and effective ways. Okay, thanks. That's the end of my presentation today. If you are interested in the work I presented, please feel free to drop me an email or visit the project website.